They resigned or what?
She resigned like I think a few weeks ago.
Okay, acha. So today you had a class with which new teacher or the old teacher only?
A new teacher.
New teacher. So in the last class, okay, so we did till ionization enthalpy, right? Okay, and by the time, can you please message others? Faisal, you please message Ahmed, and Amalia, you message Sania, Fatima, Nazira. Okay, then we will start.
Yes, sir.
Assalamu alaikum, sir.
Walaikum assalam. How are you, Ahmed?
Sir, good. How about you?
I'm also good. Alhamdulillah. Okay, Abir is also here. How are you, Abir?
Sir, I'm fine. What about you?
Good, thank you. Okay, so wait for Sania, Fatima, and Nazira. So Amalia, did they reply? The girls?
No, sir.
No. Okay. So, let us start. And today we'll start with the enthalpy of atomization and metallic character. We will discuss these two things together. So we have done atomic radii, ionic radii, and then ionization enthalpy. This will be fourth point, I think. Okay, so here we have metallic character. Metallic character and enthalpy of atomization. Okay. So how good a particular type of metal is our D block elements, and what is the enthalpy of atomization for the D block elements? Okay, for the D block elements. Now, one thing is for sure that all the elements in D block, they are metallic in nature. Okay, so all D block elements are metals. They are what? They are all metals. Now, when I look at the metallic character, then I can say that, see, a particular metal, I can say it will depend on how good is the metallic bond, right? So we have two metal atoms and they are having some free electrons. And due to this free electrons, there is some metallic character there. Okay, some metallic character there. So now when I look at the electrons, let me write the group, the 3D series. We have Sak, T, V, Pra, Man, Fe, Ko, Ni, Ku, Zan. Okay, so Scandinavian, this is 3D1, 4s2. This is D2s2. This is D3s2. This is D5s1. Manganese is D5s2. Iron is D6s2. Copper is D7s2. Nickel is D8s2. And cobalt is D7. Copper is D9 and D10s1. And zinc will be how much? Zinc will be D10s2. Okay. Now let us look at the unpaired electrons. Okay, let us look at the unpaired electrons. So we have talked about two things, the elements and their electronic configuration. And from that, we can also talk about the unpaired electron. So these are our elements, the electronic configuration, and then unpaired electrons. So here you can see S2, it is what? S2 is paired. So we have only one electron, that is the D1 electron, which is unpaired. So we have one electron in scandium, which is unpaired. Then in titanium, we have the D2. These two are will be unpaired. S2 is what? Paired. In vanadium, you can see 3. Chromium, you can see how much we have 5 plus 6, right? Because S1 is also unpaired, D5 is also unpaired. So we have how much? 6 unpaired electrons. Then in manganese, the S2 is paired, the 5 electrons in the D is unpaired. Then we have here we can see S2 is paired and in D6. So how will you write D6? If you remember something from the 11th standard, then D6 is 1, 2, 3, 4, 5, 6. So we have only 4 unpaired electrons, right? So here we'll be having only 4 unpaired electrons. In cobalt, we will be having 3. Nickel will be having 2. In copper, we have the D10, which is completely paired. S1, so we have 1 unpaired electron, and zinc, we have 0 unpaired electron. Okay, we have 0 unpaired electron. Now you can see here, that we have more number of electrons. We have more number of electrons here, right? Most of the unpaired electrons are in chromium and manganese, And as we go further down, what happens? The electropositive character is decreasing. So one thing you will write is the electropositive character gradually decreases. The electropositive character gradually decreases on moving left to right. In a series, on moving left to right in a series. That means slowly the metallic character is decreasing. And that is why you can see we have S block, then we have pure metals, okay, only metals we have. Then we have D block. So in this D block, the metallic character slowly decreases and it transitions to the P block elements where we find most of the non-metals, right? So in P block, we find most of the non-metals. So we can say that here we have the highest metallic character. In the T, we have a transition of metallic character from very high to slowly lowering the metallic character, and P block we get the non-metals also. Okay. Next is how are the bonds? Okay, how are the bonds? So you can see that if we talk about the bonds or the hardness of metal, the hardness of metals depends on the number of unpaired electrons, between the metal atoms. So we know that when we have unpaired electrons, they can overlap with each other and they can form bond, right? So if we have more number of unpaired electrons, then we have 2 metal atoms. This is 2 metal atoms means the metal atoms of a same element. Okay, so we have these 2 metal atoms, and here if we have more number of unpaired electrons, there will be a high bond strength. So it depends on the number of unpaired electrons. So if we have more number of unpaired electrons, then the metal will have a strong metallic bond, and then it will be said that it is a hard metal, right? It is a hard metal. So what can you say? So here is the beginning of the series. Here we have the end of the series, right? We have the end of the series, and we can say now that these are the metals, like in the middle, which have the highest number of unpaired electron, and that is why these will be the hardest. Yes or no, guys? Tell me.
Yes, sir.
Okay. So greater the number of unpaired electrons, greater is the number of bonds, and therefore greater is the bond strength. Okay. If they ask you a reason, so how are we going? We are seeing that greater the number of unpaired electrons, greater the number of bonds, and hence greater is the bond strength. Greater is the bond strength. Okay. So hardness in B block is highest in the middle. Highest in the middle. Okay. So you can see that's chromium. Okay. So chromium, and after that you have molybdenum, and then you have tungsten. So chromaton, chromoton, chromo, and for tungsten, which is shown by W, chromoton, have maximum number of unpaired electron, and therefore are very hard metals. Are very hard metals. Okay. Now those metal which have a very, those are which are very hard. So let us say that from M solid you are converting into M gas. So this is the enthalpy of atomization. Okay, this is the enthalpy of atomization. Now those metals which are hard, their enthalpy of atomization will be also very high, right? So the enthalpy of atomization will also be very high. So you can write that delta H naught A is directly proportional to the metallic bond strength and this is directly proportional to the number of unpaired electrons. You can also say chromoton as the highest delta H naught A. Okay, enthalpy of atomization. Okay, then when you look at zinc, so after zinc you will have cadmium and mercury. Okay, so Zn, Cd, Hg, all of these are in the same group. They all will have D10S2, and that is why they will be soft. And you know that mercury, right? Mercury is so soft that it is liquid in room temperature. Okay, it is liquid in room temperature. So zinc, cadmium, and Hg don't have unpaired electrons. They don't have unpaired electrons. Therefore, these are not very hard and have low delta H naught A. That is enthalpy of atomization. Okay, so write this down. Let me know if I have to scroll up or something.
Yes,
Sir, could you scroll up?
Let me know if I have to scroll up more or something. So इतना लिखिए आप लोग यहाँ पे. Let me know if I have to scroll down.
Sorry, could you scroll down?
Yes, sir.
What about others? Done?
Yes, sir.
Alia, Fatima,
Yes, sir.
done? Okay. Fatima, what about you?
Yes, sir.
Okay. Right, next, melting and boiling points. Melting and boiling points. Okay. Now, when we talk about melting and boiling points, a general statement would be that since they are metals, so they will have high melting or low melting points. Tell me.
High melting point.
Yes. So D block metals of high melting and boiling points. Okay, high melting and boiling point. Now, what is the trend? What is the trend in a series? So, okay, what is the trend in a series? In a series, that means 3D, 4D, or 5D. In a series, the melting points, what will happen? They will slowly increase because we are increasing the number of unpaired electron. And if you are increasing the number of unpaired electron, there will be more bonds between those atoms, and separating those atoms will be difficult. So as the number of unpaired electrons will increase, the melting point will also slowly increase. In a series, the melting point, we say, rises to maximum. Rises to maximum value around middle. And then decrease with increase in atomic number. Okay, so this is the observation. The next observation that has been seen is that we have manganese, and then we have one element which is known as tectinium. Okay, manganese, and we have one element which is known as tectinium. These have a very high, so we have manganese Mn. Okay, and then we have tactinium. These have relatively manganese and tactinium have relatively low melting points. They relatively have low melting points. Okay, now first of all we'll understand that why is this happening. Rises to maximum value around the middle and then decreases with increase in the atomic number. Okay, so tell me why it is happening. Why is the melting point increasing as we reach middle?
Because the metals are strong.
No, metallic bonds. Why are metallic bonds strong? So the sole reason will be what? Sole reason will be
Unpaired electrons are
unpaired electrons. Okay. So जब भी ये आए metallic bond, melting point, boiling point, atomization, or the hardness of metal, the main word here is always what? The main word here is the unpaired electrons in the valence shell. Unpaired electrons in the valence shell. Okay. Due to increase in the increase in unpaired electron, due to the increase in unpaired electron in valence shell, metallic bond strength increases. Hence, melting point also increases. Now, next is why is manganese and titanium. These have. So you can be asked with regarding this manganese because it is in the 3D series, and more focus and specific questions are asked in about the 3D series. So why manganese? It has low melting point. So since manganese has electronic configuration of 3D 4s2 3D 5, which is quite stable, and due to this nucleus holds the electron effectively, making it unable to form bonds, making it unable or unavailable for delocalization Okay, and if the electrons are not delocalized, they will not form effective bonds. Okay, delocalization means when you have a particular metal and those electrons in the metal, they are shared by two different atoms. So when it is shared by two different atoms, then only there will be delocalization. But manganese nucleus, it surrounds the electrons which are surrounding the manganese nucleus. They are pulled by the nucleus more effectively because of this stable electronic configuration. And that is why these are not available for other atoms for the bond formation and for delocalization. And that is why the metallic bond strength is quite low here. And hence it has low melting point, making it unavailable for delocalization. Hence, metallic bonds are weak in manganese. Let me know when you are done. Okay, one more point just regarding mercury now. Hg is, mercury is liquid in room temperature.
Sir.
Then all of you?
Sir.
Yeah, tell me.
Sir, could you explain the last point regarding the bond, metallic bond of manganese?
Manganese.
Yeah.
So manganese, it has a stable electronic configuration. That is the first thing, that it is 4s2 3d5. Okay. So you understand why it is stable? This configuration is stable, right? Why?
Yes, sir. Because
Ah.
it has only one unpaired electron.
नहीं, one unpaired electron तो नहीं है यहाँ पे.
5.
5 unpaired electrons are there, but that is not the reason for stability. Electronic configuration 4s2, it is fully filled or half filled? Tell me. 4s2 is
Fully filled.
fully filled. 3d5
Half filled.
half filled. So both of these are what? Both of these configuration are, these have extra stability, right?
Yeah.
Okay. Now, when these are extra stable, what does that mean? There are two kinds of stability. Okay, there are two kinds of stability. One is, if I heat something, will it break down? Yes or no? That is one type of stability that I think about in terms of thermodynamics, because when we are heating, that is in terms of thermodynamics. Then the next type of stability is these electrons. Now, if these electrons are effectively pulled by the nucleus, there is more and more attraction between the electron and proton. Then we say that due to this high attraction, this whole configuration is stable. This whole configuration is what? It is stable. Okay. Now, in this case, when these electrons are effectively pulled, now that is why this is extra stable, because it is only dependent on the electronic configuration. So with the electronic configuration, I'm saying it is extra stable. That means these electrons are effectively pulled by the nucleus. Got my point till here?
Yes, sir.
Okay. So now we have concluded that these electrons are pulled by the positive charge, that means the nucleus, more effectively and very effectively. I mean, relative to the other, if I compare with the other elements, then I can say that these are effectively pulled by the nucleus. Now, if something is pulling the electron, this will make these electrons a bit of unavailable now for bond formation, because we have this proton which is pulling it, and that is why these electrons are more near to the proton, and that is why these electrons cannot be shared by any other atom. Correct? So there will be less bonds.
Yes.
If there will be less bond, the metallic bond will be weak or strong?
Weak.
Weak. And if the metallic bond is weak, then it will be easier to convert it to solid. Sorry, convert it to solid to liquid, from solid to liquid, right?
Yes. Yes.
Solid to liquid will be easy, right? So that is why they have low. Here we have written magnesium and technetium have relatively low melting points. That is the reason. Same reason is for technetium, but you will be asked directly from manganese, not from technetium, because this is not in the 3D series. Okay, but the answer is same here also. Technetium also have a similar electronic configuration. We have these elements, manganese, then below that we have Tc, and then we have Re. So all of these elements, they have relatively low melting points. The reason is S2D5, S2D5 configuration. Let me know if you're done. Then we will do oxidation states.
So can you go to the
Electron,
electronic configuration?
electronic configuration कहाँ लिखा हमने? यहाँ ये. अच्छा.
Yes, sir. Sir, the unpaired electron, how do we count that? Like for the first one, we have 1.
अच्छा. So you have 3d1 and 4s2 ना, and then here you will have argon. सही है?
Yes, sir.
So you remember ना the boxes, right? This is 3d. 4s2 will be like this. So how many unpaired electrons?
Yes, sir. Clear.
Got it ना? ठीक है.
Yes, sir.
Done with this, guys. अमल्या, फातिमा, अरे बताइए, आप लोग तो शांत ऐसे बैठे हुए बिल्कुल. Yes, फातिमा, done.
Yeah, sir.
Okay. So next is oxidation state. Melting point means sixth is oxidation state. Okay. So in oxidation state, let me show you the type of oxidation state these elements they show. So I'm talking here about the 3D series only. Okay. This is visible, right?
Yes, sir.
Okay. So now you guys see, we start with scandium, and in scandium we have +3 oxidation state. Then we go to titanium, vanadium, chromium, manganese, Fe, cobalt, nickel, copper, and zinc. So except if I leave scandium, then all of them, what is the common oxidation state in the 3D series? +2, right? Yes or no?
Yes, sir.
All of these elements have +2 oxidation state. Okay. All of these elements, they have +2 oxidation state. Now, why do they have +2 oxidation state? Because the common, what is our, here we have, so in the 3D series, in 3D series, the electronic configuration is, we have 3D 1 to 10 and 4s2. Okay, and 4s2. Now this 4s2, the 2 electrons in the s orbital, this is why now all of these have 4s2, right? And this is the reason why we have +2 oxidation status, the common or the most common oxidation state. Common oxidation state in D block elements. Okay, so one question will be, why is +2 oxidation state most common oxidation state in the D block elements? Then you will say that now in 3D series, this is the order, but if I talk about the D block, so in D block elements, I can say it is n-1d 1 to 10 and ns 1 to 2. So this is the general electronic configuration for the D block elements. Now, since the S2, the S subshell, it has 2 electrons in the D block element generally, that is why +2 is the most common oxidation state. Okay, so most of the elements, they have ns2 configuration. That is why +2 is the most common oxidation state in the D block elements. Okay, so this is clear, yes or no? Why it is +2?
Yes, sir.
Okay, now next is why they have variable oxidation state. Why do they have variable oxidation state? So this is due to the n-1d electrons. Okay, n-1d electrons. Okay, so the oxidation states are due to 2 things. So you can write here variable oxidation state is exhibited by D block elements due to the comparable energies of n-1d subshell, S1d and ns subshell. Okay, this is the reason. Like both of these subshell, they have electrons, and those electrons can be shared, and those electrons can be used for the bond formation. They can be used for the bond formation. Okay, next is. Okay, next you look here. Where do you see we have the maximum oxidation state? Which element?
Manganese
Manganese. How much it is?
+7.
5.
+7. Huh? So now that is also very much clear. If I look at the electronic configuration, we have 3d5 and we have 4s2, correct? Yes or no? So these
Yes, sir.
two electrons, when only these two electrons will be in the bond formation, then it will have +2. When one of the electrons from 3d, then it will have +3. When another electron will be shared, then it will be +4, and so on. We can have till +7 oxidation state. Okay, till +7 oxidation state. Chromium also you can see it as why, because we have 3d5 4s1. Okay, so when two electrons are not there, then we have +2 oxidation state. When we have removed 3 electrons, then you have +3, and in total you have how much? +6 oxidation state. Okay, you have +6 oxidation state. Okay, so these are the points that we will write now. First of all, you draw this complete thing and write the initial points.
So we have to draw the table.
हाँ वो एक बार ड्रॉ कर लीजिए ना.
Yes, sir.
Alia, Fatima, done.
No, sir. One second.
1 second, sir.
Okay.
So what is the last point you wrote? Variable oxidation status.
Exhibited. Shown by.
By d block element due to the comparable energies of n-1d and
NS subshell. NS.
ns.
Done now, all of you? Yes or no?
Yes, sir.
Okay. Good. Right, next point here. The variable oxidation state is exhibited due to the participation of comparable energies of n minus d and ns subshell, n minus s subshell. Next is, when I look at scandium, one of the observations is when I look at scandium, it doesn't have any +2 oxidation state. Okay, it has only +3. But after this, we have +2 oxidation state. After this, we have +2 oxidation state. What does it mean? So in scandium, we have argon. Then there is 4s2 3d1. Okay, 4s2 3d1. And after that, if I look at vanadium, it is going to be argon 4s2 3d2. It means that since scandium shows +3 oxidation state, it shows that this d1 electron, it is what? It is unstable and it can be easily removed. Yes or no? Can be easily removed.
Yes, sir.
Right? It can be easily removed. But when I look at vanadium, it starts with +2. It has the +2 oxidation state. It means that there is a bit of stability in these d2 electrons, So what we can conclude from here? We can conclude that except scandium, all other elements of 3D series show +2 oxidation state. It means that the stability of d electrons increases after scandium. After scandium. This is clear, yes or no? Please tell me.
Yes, sir.
Right. So this is what we have concluded from the +3 oxidation state of scandium, and then we don't get any +3 oxidation state. So we can say that after scandium, what is happening? The stability of d electron is increasing. The stability of d electron is increasing. Next point is,
So can you scroll a little up?
आप पूछ रहे हैं क्या?
No, sir, this point only.
अच्छा, वो हम लिखा देंगे ना, एक पॉइंट हो गया, टाइम दे देंगे. ओके अबीर. Next point is, now where do we see the highest number of oxidation state? The highest number of oxidation state is, rather I can say, occurs in the middle of transition series. Occurs in the middle of transition series. Okay. Now, next thing that you can see about the highest oxidation state. Okay, highest oxidation state. So scandium, it has 3d1, 4s2, है ना? Titanium, it will have how much? It will have 4s2, 3d, 4s2 and 3d, how much? 2. So it has 3 electrons. Okay, it has valence 3 electron. Titanium has 4 valence electron. Vanadium has 5 valence electron. Chromium has 6 valence electron, and manganese have 7 valence electrons. Okay. Now when I go to iron has 4s2, 3d, 4s2, 3d, how much?
3d4.
6 now. Scandium 1, 2. Here we have 21, 22, 23. Now, so this will be 3d6.
Yes,
This is
sir, yes.
3d5. So here, how many valence electrons are there? 8 valence electrons are there, but we don't get +8 oxidation state from iron. What does that again mean? It means that as we go from scandium to zinc, what is happening? The d electrons, these are getting more stable, and that is what we have written here. Except scandium, all the other elements have so +2. It means that the stability of d electron increases after scandium. After scandium, what happens? The d electron stability increases, and that is why we don't see anything. The maximum oxidation state in the first series. Okay, so starting from scandium to manganese, the maximum oxidation state is equal to the number of electrons in Ns and Nd electrons, N minus 1d electrons. So you can write another conclusion in the observation side that the maximum oxidation state, shown by the first 5 elements of 3D series is equal to sum of Ns and N minus 1d electrons, But as we move further on, okay, that means after manganese, okay, we don't have, after the manganese, the maximum oxidation state, it is not equal to the sum of Ns and N minus 1d. That means we can say it is not related to the electronic configuration, okay, it is not related to the electronic configuration. The next 5 elements have minimum electronic configuration of +2 due to the 4s2 electrons, but the maximum oxidation state is not related to the electronic configuration. Okay, so I can start writing from here. Let me know if I have to scroll down.
Sir, could you scroll down?
Let me know if you're done. Kabir is done. Malia is done. Waiting for Ahmed, Fatima, Faisal.
Yes, sir.
Done. Write the question. Which of 3D series elements? 3D series. Transition metal. Shows highest oxidation state, or rather I should say largest number of shows, largest number of oxidation state, and why. So answer will be is manganese. Okay, and why? Due to high number of unpaired electrons in D subshell. Okay, in D subshell. Next, that is standard electrode potentials. So which number is this? We have done 6th and 7th property. Standard electrode potential. So just a recap, standard electrode potential. Standard electrode potential is standard reduction potential. By convention, okay? By convention. By convention of IUPAC, standard electron potential is what? It is the standard reduction potential. And since we have metals in D block elements, in general, the D block elements since they are metal, what they will do, they have a tendency to, in general, D block element have tendency to lose electrons. They have a tendency to lose electrons. Okay, why? Because of the metallic character. Because since they are metal, they will lose electrons. They will be losing electrons. Okay. Now, next is, so their electrode potential. That means the standard reduction potential will be positive or negative. Tell me, what will be their standard electrode potentials?
Positive.
Positive.
Positive, right? Hence, standard electrode potential or SRP, standard reduction potential of D block elements are usually positive. Now, in this D block elements, when we talk about the losing of electron, right? They will lose electron. And when we talk about electrode potential, so we talk about M converting to, which is solid, right? Generally we have solid, it gets converted to M plus, right? And here we'll be looking at M2 plus because this is the most common oxidation state. So when a metal, it gets converted into 2 plus in aqueous state plus it gives 2 electrons, plus it gives 2 electrons. So this is what's known as the electrode potential. Here we see what? Here we see we have 2 electrons, and M is what? M is in aqueous state. M is in aqueous state. Now, there are a few reactions. There are a few steps involved here. First of all, this metal, it has to get into its isolated state. That means I have to isolate each and every atom of metal, so that I will make it, first of all, gas. When I go from M solid, that is a metal which is solid, and I convert it into gas, I'm talking about the enthalpy of sublimation. Now, next, what I have to do, I have to ionize it, right? I have to convert this isolated gaseous atom to M2 plus. Okay, this is also gas and this is also gas, isolated gaseous atom. Okay, now from M2 plus, I have to convert it into aqueous. That means I will add this gaseous atom into water, and this is okay. This is delta H I, that is ionization enthalpy, and this is the delta H of hydration, right? Hydration enthalpy, because when I add something to water, the oxygen which has negative charge, right, H2O, there is delta negative right here, and when I add M positive, so there will be M2 positive, and they will be interacting. So this is a favorable thing, right? The delta hydration, it is what? It is favorable. It is giving interactions. So when I go from M solid to gas, I have to give energy. When I have to remove electron, I have to give energy. But this hydration enthalpy is what? Hydration enthalpy is a stabilizing effect. Okay, this is stabilizing effect, and there is attractive forces involved here. Okay, attractive forces involved here. So for a metal, if I want something for a metal, to be strong, now it is what? It is losing electrons. So iska to kya ho raha? Oxidation ho raha hai. Then metal will be a reducing nature, right? So for a metal to be strong reducing agent, there are 3 things happening, right? The delta H sublimation. So you tell me, we have to give energy or take energy to go from solid to gas?
Give energy.
Give energy. Ionization ke liye kya chahiye? Okay, if I want to give energy, then what? It should be high or low? If I want a
High.
strong reducing agent. अच्छा, अगर हाई होगा तो आसानी से हो जाएगा या दिक्कत से होगा? It will be easy or difficult if the sublimation energy will be high, enthalpy of sublimation will be high, then it will be easy to convert or tough to convert?
Easy.
Are enthalpy of sublimation
No.
is high, then we have to give more energy, na?
Yes.
Then it will be more difficult, na? And we want to go from M to M2 positive, right? We want to oxidize the metal, and that is why it is giving 2 electrons. So these 2 electrons will be eaten by something else, and that is why metal is of reducing nature. Metals, they reduce others and they get oxidized themselves. Okay, so this is a reducing agent. It doesn't get reduced, it oxidizes itself and reduces others. And if it wants to reduce others, then the delta H sublimation should be low. Next is ionization enthalpy should also be low, right? Because here also we are giving energy, correct? Yes or no?
Yes, sir.
Next is delta H ionization should be low. And enthalpy of hydration, it is what? It is a stabilizing effect. Okay, it is a stabilizing effect because there are attraction involved. If we have more hydration enthalpy, that means that particular hydrated ion is what? It is more stable. So you should have magnitude of delta H hydration should be high. Okay, so all of you got this? Yes or no? First of all, tell me that. These 3
Yes, sir.
steps and the information here. Okay, no. Delta H, that is from here to here, M to M2 positive. So you can write the enthalpy change that is involved in the reduction. It is equal to the delta H of sublimation plus the delta H of ionization plus the delta H of hydration plus the delta H of hydration. Okay. So if this delta H is small, that means we will be having a good reducing agent. If this delta H is very high, then we'll be having a bad reducing agent. Okay, so one of the questions that you get is when you see copper, when you see what? When you see copper. Let me read the question. The E naught of Cu2 positive. Okay, ऐसे नहीं होगा. E naught of Cu is Cu2 positive to Cu is 0.34. एक तो आप लोगों ने उल्टी चीज यहाँ पे लिखा दी. Yeah, correct. This is positive, correct. Cu2 plus to Cu is 0.34. ठीक है? It is what? It is 0.34 volt. Okay. Why? So see here. Here we are having M to M2 positive. So this is what is happening here. This is oxidation is happening, right? Oxidation is happening. So the reducing the D block usually have is positive. So you look here and tell me, why is this positive? What does that mean? Cu2 positive is minus 0.34. Correct? Yes or no?
Yes, sir.
Okay. Now, if it is minus 0.34, then what I can say about this reaction? Will it happen easily or not?
Yes, sir.
It will happen easily.
No.
Electrochemistry भूल गए. If SRP is positive, then what does it mean? Reduction.
Easily.
That means reduction is spontaneous. है ना? And if SOP is positive, then oxidation is spontaneous. Right? Yes or no?
Yes.
है ना? Okay. So उसी से हमको याद है, yeah, exactly correct. We have written this thing wrong. चलिए एक चीज आप लोग बताइए. This is oxidation or reduction?
Oxidation.
Oxidation. So metals, they will get oxidized easily, yes or no? If they are metals,
Yes,
they will
sir.
solve this reaction easily, है ना? So
Yes, sir.
oxidation
Yes.
is easy. So oxidation is easy. That means SOP for metals is
Spontaneous.
and that is why SOP will be positive.
Positive.
Okay. Now SRP will be, if SOP is positive, SRP will be
Negative.
negative. Okay. So I think we wrote this wrong. इसको change कर लीजिएगा. No, I don't think you have written this. No, it's negative. Okay. Standard electrode potential. Now, the standard electrode potential of most of the metals are negative, but here it is what? Here it is positive. Now, why is that? We have to talk about why is that.
Sir.
Yeah, tell me.
So what is SOP?
Standard oxidation potential.
Okay.
SRP is reduction potential. OP is oxidation potential. Okay. Now, it means that this reaction is non-spontaneous. Okay, what does this mean? Cu2 positive to Cu is 0.34. Why? So if Cu2 positive to Cu is 0.34, that means Cu to Cu2 positive. That means the oxidation reaction is what? Negative. And hence Cu2 Cu2 positive aqueous is non-spontaneous. Now we know that we have three different type of reaction happening. So we will have copper first of all. It will convert itself to copper gas. Then I will convert this to copper 2+, and after that we will do copper 2+ aqueous. Right? Copper 2+ aqueous. Yes or no?
Yes, sir.
This is delta H sublimation. This is delta H ionization, and this is delta H hydration. Now, this delta H sublimation and enthalpy of ionization. These will be low. Yes or no? Because copper is what? Copper is argon 3d10 4s1. Yes or no? Now you tell me how many unpaired electrons are there in copper? How many unpaired electrons?
1.
1. Okay, it has 1. So it means that I can easily go from copper solid to copper gas. Yes or no?
Yes, sir.
Yes, sir.
Right. So this is low. Okay, this is low. Now let us talk about enthalpy of ionization. Okay, enthalpy of ionization is what? If I will go from copper, if I write copper 2+, this will be argon 3d9. Yes or no?
Yes, sir.
Right, 1 electron from the S and 1 electron from the D. Now you tell me, this will be high now because we are going from stable to very unstable. We have D10 here and 4s1. This is fully filled, this is half filled, and we are going from fully filled, half filled, extra stable thing to what? 3d9. 3d9 is what? 3d9 is neither half filled nor full filled. It is incompletely filled. That is why it will be very high. It will be very high. Okay, it will be very high. Now, next is the hydration energy. Now, hydration energy, you have to go to the data, and hydration enthalpy is low. Okay, which should be high because if hydration is high, that means it is stabilizing effect. Now, copper 2+, so stabilizing is low, and that is why. So the reason is two. The reason is first of all due to high enthalpy of ionization and low enthalpy of hydration. Okay, these are the two reasons. Delta Hi is very high because we are going from stable to unstable, and hydration enthalpy you have to take the value, okay, data value, but that it is low. Copper 2+ hydration enthalpy is low. This is the reason you will write due to high ionization enthalpy and low enthalpy of hydration. Okay, low enthalpy of hydration. Okay, so you will start writing from here, right?
Sir, 7 number point you wrote standard electrode potential. It will be potential.
And potential. Sorry, my bad. Done guys, yes or no?
Sir,
Yes,
can
sir.
you scroll down?
Yeah, sure. Done guys?
Yes, sir.
The complete thing, yeah, this question also?
Yes, sir.
No, sir. Writing the question.
Okay, okay. Done guys?
Yes, sir.
Okay. Now in standard electrode potential, we'll also learn about. So we looked at the M to M2 positive, right? Here we are looking at M to M2 positive. Now we will also look at the standard electrode potential of when you have M3 positive to M2 positive. Okay, that means we are talking about reactions such as, so SCP of M3 positive to M2 positive. Okay, that means we are going from, this is standard electrode potential, that means it is what, SRP. This is SRP. Okay, this is SRP. So what will be the SOP reaction? Standard oxidation potential will be M2 positive to M3 positive, right?
Yes.
M3 positive. Okay, so this will be SRP for this. SRP for M3 positive and M2 positive. It is like have titanium, vanadium, chromium, manganese, iron, and cobalt. Manganese, iron, and cobalt. So here we have minus 0.37. These are the SRP values. Okay, SRP. If it is minus, that means they don't want to get reduced. They will oxidize easily. So titanium will oxidize easily. Vanadium, it also has minus 0.26. Chromium also has a minus, that is 0.41. Manganese has a very high, plus 1.57. We will look at the reason here. Also, iron, it has plus 0.77. And cobalt, it has plus 1.97. Okay. Now, there are two things that we will look. First of all, why do these? Manganese, it has low, right? Then we have iron. Now, iron is also what? Iron is relatively low, right? Iron is relatively low. If I look at manganese and cobalt, iron is relatively low, and then cobalt we have 1.97. So we'll talk about iron first of all and manganese. Why does manganese have a high thing? Okay. So first thing is that number one, if I go from Mn2 plus to Mn3 plus, Mn2 plus to Mn3 plus, then we are going from, this is argon, (3d5) to argon 3d4. Correct, guys? This is very stable. This is unstable. If I look at the electronic configuration, correct? That is the reason why
Yes.
manganese has a very high positive value. Okay, very high positive value. That means it readily wants to go the reverse reaction. That is, it can easily go to M3 positive to M2 positive. Okay, this is the feasible reaction for manganese. This is the feasible reaction. That means reduction. Okay, this means reduction for manganese. Next is, why does iron has relatively low? Okay, so the reason due to a reason for high positive SRP of Mn. Okay, is D5. Okay, is D5. Next is, if I look at Fe, so we have Fe 2 positive. It has the electronic configuration of argon 3d5. Yeah, argon. Wait a second. This will be argon 3d6. Then Fe3 positive will be argon 3d5. Okay, so here we are going from unstable, that is not half filled, to half filled. Okay, so since Fe3 positive is half filled, it is more stable. Okay, it is more stable. So these are the two observations that you have to look. Okay, that you have to look. Now there is one question which is related to a bit of coordination chemistry. Okay, so let me write this question. The question is, which is stronger reducing agent Just wait 5 minutes. Can you wait 5 minutes, Fatima? I will just leave after this question. Okay, Fatima. Yeah. Which is stronger reducing agent? Cr2 plus or Fe2 plus? Okay, and the question is why? Okay, also why? Which is stronger reducing agent? Now here you have to first of all write the reduction reaction. Okay, the reducing agent. Now, so you will write the Cr2 positive and Fe2 positive. It is giving electrons. So you have Cr2 positive gives electron, forms Cr3 positive plus electron, and we are going from Fe2 positive to Fe3 positive plus electron. Okay. Now, when you look at the electronic configuration at Cr2 positive and Fe2 positive, so for Cr2 positive and Cr3 positive, right? So we have Cr3 positive and Fe3 positive. Now, when you look here, so Cr3 positive has an electronic configuration of argon. 3D, how much? Tell me. Chromium is 24. Right? Chromium is 24.
Yes,
So
sir.
we have removed 3 electrons. So 3D, how much?
3D,
3D? 3, right?
3D.
They had 2 plus 4. ऐसे कर लीजिए, देखिए. Look here. 4 plus 2 is how
3D.
much? 4 plus 2 is how much? 6, na?
Yes, sir.
So there are 6 valence electron in chromium. Okay, there are 6 valence electron. And in 6 valence electron, how much we have removed?
3.
3 electrons, right? So how much will be remaining? 3. And we first fill 3D, so 3D3. Okay, 3D3.
Yes.
Now let us look at iron. Now in iron we have Fe3 positive. So argon is how much? Fe is 26, right? You remove 3
Yes,
electron. So 6 plus 2 is 8, 3D5. Now you tell me which one seems more stable, Cr3 positive or Fe3 positive?
Fe3 positive.
Fe3 positive.
It seems more stable, right? But what it is saying, but here what we see that Cr3 positive is more stable, I can say that Cr2 positive is of higher reducing agent and Cr3 positive is more stable. The reason is, listen to the reason. When I have this in aqueous solution, now this will be aqueous. So the Cr3 positive, it can coordinate with H2O, right? It can coordinate with H2O, okay? And when it coordinates with H2O, there will be splitting of d orbital, correct? So we have the 3D. Okay, so 1, 2, 3. Then there is splitting like this. Okay, there will be splitting like this. And here we have T2G, here we have EG. You remember these things, yes or no?
Yes, sir.
Splitting of d orbitals, coordination complex. Right, Abir, Ahmed. Splitting yaad hai, nahi yaad hai?
Yes, sir.
T2G and EG. So when you have 3 electrons here, all of these electrons will be in the T2G orbital, right? T2G orbital.
Yes,
so this is lower in energy, right? T2G is lower in energy. Okay, so we can say that Cr3 positive, Cr2 positive is better reducing agent as Cr3 positive is more stable in aqueous medium due to T2G3 electronic configuration. Okay, so please write this down. If you write this one line only, this will be enough. This was only for explanation that there will be EG and T2G. Okay, so ये आपका जो सवाल आएगा, this will be like for 1 or 2 marks. So please remember this question. If they ask about reducing agent of Cr2 positive and Fe2 positive, then you will bring in the T2G3. You will bring in the T2G3 reasoning. Okay, Cr2 positive is better reducing agent as Cr3 positive is more stable in aqueous medium due to the T2G3 electronic configuration. And why T2G3 is more stable? Because it is half filled, right? It is lower in energy and also it is half filled.
Sir,
Yes, sir.
Yeah, tell me.
sir, what is T2G3?
You have done coordination. Oh, आपने नहीं किया होगा ना वो? Because you have only learned term 1, na?
Yeah.
Okay. So in coordination complex, there is one theory in which splitting of d orbital happens. Okay, splitting of d orbital happens. अभी इसको लिख लीजिए, है ना? And I think you can ask Nishkar sir with the for the videos of coordination complexes. Okay, in that only we will explain, because this is complete one complete lecture. I think I may have notes. You can get notes from Nishkar sir. Okay. यहाँ पे देखिए, like it is complete theory, है ना? EG, T2G, splitting of orbital in octahedral, tetrahedral, है ना? So I would have to explain many things in the crystal field theory. Okay. वो अभी लिख लीजिए बस आप, but after that you can ask the notes or the lecture also from Nishkar sir.